Okay, so now let's move on to the second question. Well, the third in the exam. Magnetically coupled circuits. This is what I would say is the hardest or second hardest, depending on how you find Laplace transformations. The first one is chat recorded sometimes. Am I going to do question one? Question one is just second order RLC. I already did that for my midterm thing, and we're not getting it on our final anyway, so I didn't do it. Yeah, because it's midterm. We're not doing midterm stuff on the final. So, write a loop equation describing the left-hand side of the loop. This stuff is super simple. It is KVL. The only stuff that is slightly hard is this stuff that you call magnetically coupled coils. So, to do magnetically coupled coils, first look at the dots. In this case, they are opposing, right? Will I do any transformers? I'm doing the transformer in here, just to make sure because I'm not too sure. Did they cover T transformers and pi transformers, or just T transformers? Does anyone know? Okay, so they definitely did do T. Well, I'll do the T. If someone knows, then they can tell me at that point. So the way that I do it, first of all, keep your currents in counterclockwise. It just makes things easier. So we look at these ones here. They are magnetically opposed. All right, magnetically opposed. So the way that actually a better way to think about it. Let's draw out a big blown up diagram of this. I do the dependent source method because I just prefer it. This is going to be I1 and this is going to be I2. Yeah? And we have our dots. They're opposed. When they are opposed, and just need to make sure because I also fuck up on the dot a lot. When they are opposed, would it be different if it was 80? Yes, it would be different if it was aiding. That's the point of the dots, is to show you if it's opposed or aiding. And I'll show you aiding in a second, but let's start with opposed because that's what the question gives. Actually, no, fine. Let's work with aiding. Aiding, and then I'll show you opposed first. Side by side. So here's opposed. And here we have aiding. It doesn't matter if the aiding is on the opposite side as long as they're aiding, right? If both dots were down here, it's still aiding. It's the same process. If the pins that we're opposing were like this, it's the same process as opposing. The only thing that matters is if they're not on the same side, right? If they're not on the same like this point. You get what I mean. Okay. So if it is aiding, that means that it's helping the current that you're looking at. So in this point, the current is flowing down, right? So the dependent sources will also be pointing down. It's going to be positive on the bottom, negative on the top. The other way to think about it, it's going to be the opposite of the other current. So you can see this current's going up, the dependent source will be pointing down. And that's actually, I think it's a proper way to do it. We look here, it's aiding. We do the opposite of the other one. It's going to be positive up and negative down. So the voltage source is pointing up. Does everyone understand that? It does the opposite of the other current. Any confusion about that? All right. I think nobody's confused about that. Now, opposing. If it is opposing, it does the same as the opposite current. So this here is going to be positive up, negative bottom. So it's going to be pointing up. And you can see why it's called opposed, because the two currents, the voltage source is opposing the current. And once again, up here, it's going to be positive, negative here. Oh wait, no. Yeah, it's gonna be same. Sorry, it's gonna be same. So it's negative on the bottom, positive on top, pointing down. Right? It's the same. If it's aiding, it's opposite. If it's opposing, it's the same as the other current. Anyone confused about that? All right. I think nobody's confused about that. Thank God. Now we can draw our circuit here. Let's draw the actual representation of our circuit with these dependent sources involved. So on the left we have we have our voltage source of 100 with a phasor of 0. It goes through a resistor of 2 ohms, through a capacitor of negative 12J, through an inductor. And because we already solved the direction, the dot really doesn't matter anymore. Through the dependent source, back around. This, once again, is going to be positive up here and negative because they are opposing. Can you send a screenshot of the aiding and opposing? Yes, for sure. All right, so this is the left-hand side. Let's fill in the values. So this is going to be 18J. And this is going to be the mutual. So it's going to be 10J. And the current flowing through the opposite side, which in this case is going to be I2. We declare this one I1, and we're going to declare the other one I2. So let's draw the other circuit. So on this side, you're going to have, once again, your inductor, your dependent source, and 2 resistors. I know you can just combine them, but we'll do it later. This here is going to be 6J, and this here is going to be 10J I1. Once again, we draw our current here, I2. Everyone understand how we got here? I'll take that as a yes. So now that we've drawn our circuits, we can now start question A. Write a loop equation describing the left-hand side loop. This is just KVL. You shouldn't have any problems with this. KVL. Mesh analysis. It's going to be 100 volts on top here, minus 2 times the current 1, minus, or this is going to be plus 12J I1, because the capacitor, minus 18J I1, minus, because it's coming out the negative end of the voltage source, minus 10J I2. And it's treated as a voltage source, right? So it's just, you just copy the value there. Is equal to 0. And now we're going to simplify this. So we're going to have I1 times, let me pull out my calculator. Is this one? Yes, this one. Negative 2 plus 12J minus 18J, negative 2 minus 6J, plus I2, and I2 is just going to be negative 10J, is equal to negative 100. Let me just verify that with, what did I fuck up here? Oh, no, no. When I was doing the work before this, I wrote this. I wrote this as negative 16J. I don't know how I got that. I like this line is fine, but then I wrote negative 16J for that. That's awesome. I'm horrible. Yeah, this I would say this. I make a lot of very silly mistakes. I'm fine with this. I can't do algebra for the life of me. So that's our left hand loop. And now we need to do the right hand loop. Exact same thing. Just remember KVL. So let me just pull this to the other screen so I can look at it. We're going to have negative 10J. I'll just copy it here on the side so we can both see it together. What was my linear algebra mark? My midterm was a 55, and then I clutched it at the end with a B plus. I walked into the linear algebra midterm with a patty in hand because I thought the midterm was going to be at 6 to 8. And then I walked into my lecture thinking it was a lecture, but it was a midterm. Yeah, I got eaten by that fucking midterm. It was awful. Anyway, so negative 10J, we're going to start at the voltage source. So negative 10J I1 minus 6J I2 minus 5 I2 minus 3 I2 is equal 0. You all sound like so surprised I didn't do too well in the linear algebra exam. Josh got 26? What? I don't believe you. Anyway, I1 is just going to be negative 10J plus I2, which is going to be negative 6J minus 5 minus 3. That's going to be negative 8 minus 6J is equal to 0. We now have both of us. What did I get? I just told you I got 55 on the midterm. Now we have both. Oh dear. I did very well in the final though. I will say. I locked in for that. Anyway, we now have both of these equations. And now we have to do everyone's favorite task called Kramer's rule. What I got in the final, I think it was around a 90. I don't remember the exact score, but it was around a 90. No, I'm not doing substitution. I'm doing Kramer's rule. So the way that I like to do it, I like to fill out first a matrix here. This is going to be I1 and I2 is equal X, Y. Why don't I do elimination? I'm just used to Kramer's. Truth be told, whenever I'm doing it just myself, I just use MATLAB. I know I'm a little wrong in the head, but I just use MATLAB. It's easier for me. Negative 2 minus 6J. Well, technically, I don't use MATLAB. I use GNU Octave, but it's MATLAB. It's MATLAB. Anyway, you should all know how to do this. It's going to be AD minus CB. Delta 1 is going to be X XD minus minus YB. And delta 2 is going to be AY minus CX. Everyone knows how that's happening, right? You know, I'm way too lazy to draw it out. I am literally just going to copy my own work from earlier. There you go. It's a determinant of that. This is the way that I like to remember it. So I like to assign all of these variables, and I actually use them. I put them on the calculator. If you read your calculator's manual, which I recommend everyone should, for the 991 ES plus C, you can assign values to variables. You can just put in those variables. You don't need to keep on retyping it. So anyway, Kramer's rule. The determinant is A, B, C, D, right? A, B, C, D. Determinant 1, you replace the first column with the output here, with this column here, and determinant 2, you replace the second column with this. And you just compute the determinants. I1 is going to be determinant 1 over determinant. I2 is going to be determinant 2 over determinant. That's it. I'm not going to go through that because that is... I really don't want to. We are going to type it out into MATLAB. So that's going to be a -2 minus 6i minus 10i minus 100 minus 10i minus 8 minus 6i 0, and then REF it. There you go. So I1 is 10, is just 10. And then I2 is -6 minus 8j. So that's 10 with a phasor of 0. This is, what is that, -6. The only problem with MATLAB or GNU Octave, whichever you use, is that it doesn't accept phasor. You can only work in rect, which is a little annoying. Anyway, this is 10 with a phasor of -127. That's if I put the numbers right in MATLAB, and I believe I did. And so we have now determined current 1 and current 2. Oh, answer in rectangular form only. Okay, so this should be your answer. 10 and -6 minus 8j. Now, here we go. Redraw the circuit as a linear transformer equivalent T circuit and find the net impedance as seen as 100J force. So once again, I'm going to ask a question. Does anyone know if we were taught something other than equivalent T circuit? Were we taught pi circuit? Or just T circuit? I haven't been to a lecture since after mid. None? We haven't been taught... Wait, you guys haven't been taught any equivalent circuits at all? So transformers, we have... Oh, Kilgore, do you know if you did... Oh, Jasar just did T. Okay. So equivalent circuits is just the method of getting rid of the mutual method, the mutual voltage. Instead of having the mutual voltage, we instead replace it with another what do you call? With another component. So the T is called a T because it looks like a T. So instead of having like this with our dots wherever we want it, we convert it into a T junction. Like so. This is the equivalent T junction. So you'll notice that this has no, this part is why it's called a T, right? Because it looks like a T. The other one is called a pi because it looks like a pi, not an actual pi, like that. Looks more like that, really. I think. I forgot. I haven't looked at the pi yet. Anyway, so we need to convert this to the other. Now, let's do... I'm just... Y'all are crazy. Anyway, let's do KVL. So if we were to do KVL here, let's look at I1. Okay, so first of all, let's look at I1 in our mutual. What did we get here? Across these two, across just this part, because this part is really what we're looking at. We don't when we're doing the T, we're just looking at this part and we'll fill in the rest later, right? So let me just bring that down here. Let's put that off to the side. I'm going to erase it later, but just so that you can see as well. So for I1 in the mutual, we just care about this part because this is what we're replacing. We have 18. We have minus 18 mutual KVL. This is KVL. You'll see where I'm going with this in a second. It's going to be minus 18J I1 minus 10J I2. But what about this T junction? Let me just put this in orange so it's separated a bit more. There you go. What about this T junction? What we're going to get is we're going to get minus, let's call this the impedance 1, impedance 2, and then the impedance mutual, right? We're going to get minus the impedance 1, I1, minus the impedance 2 of I1 minus I2, right? Let's expand that out. We're going to get impedance 1, we're actually going to get impedance 1 plus impedance 2. Sorry. Minus impedance. Is that how it is? You know, let's just take one step at a time. I'm a little stupid. Why do you only use those in the red boxes? Because that's what we're trying to replace. If you look here, we can have whatever circuit behind these. What we're really looking at is replacing this part, which is the two inductors with mutual stuff with this T junction. That's why these little circles are here. That's to indicate there's more to it, but we're just looking at this segment, right? So we don't care about what goes on outside, what I'm saying. So we are going to have minus Z1 plus Z2, I1 plus Z2, I2. And we need to make these two match, right? Because it is an equivalent circuit. We're trying to make a circuit that does the same thing with what we started with, right? We need some Z1 plus Z2 to make ZI and Z2 to make I2. Well, let's look here. There you go. We've just found sorry. I just realized I've been using the wrong value. This is supposed to be M. None of you corrected me. I'm sad now. Right? So if I look here, this is negative 10JI2. This is plus ZMI2. So what is ZM? It's going to be negative 10J. Everyone follow this? Everyone understand how we got negative 10J here? All right, perfect. So we now know that ZM is negative 10J. Therefore, we can figure out ZI because all of this is supposed to be equal to negative 18J. Right? So therefore, Z1 must equal to 8J. Is that correct? No, that's not correct. It's supposed to be equal to 28J. There you go. 28 minus 10 is equal to 18. You apply that negative sign, you get negative 18J. So now if you fill this out with the values that we've gained, what do we get? We get negative 18J I1 plus 10J, or sorry, minus 10J I2. That's what we want, right? We have now determined ZM and Z1. Any confusion about what we just did? Helldivers 1 or 2, really? I think I see Helldivers 1 through rose tinted glasses. I haven't played it in forever, but I loved it. Anyway, now we do the exact same thing to find Z2. Helldivers 1 is what I'm saying. When I was very young, I played Helldivers 1. This guy's, yeah. Literally. Lock in, bro. Lock in. Okay. So now we do the exact same thing for I2, right? So once again, I'm going to drag I'm going to drag this diagram a bit down here. This is a bit long. My bad. I2, through the mutual design that we have here in KVL, what do we get? We have minus 10J I1 minus 6J I2. And what about in our new circuit? In our new circuit, it's going to be, let's see, I2 in a T circuit in KVL. We're going to have negative Z2 I2 minus ZM I2 minus I1. Everyone understand that? You do the same stuff. It's same exact process. Shouldn't be any confusion about it. So ZM we already know. So that's going to be negative 10J. Wait, sorry. Oh, right. Let's expand this out. So it's going to be negative Z2 I2 minus ZM I2 plus ZM I1. Now, I1 is supposed to have negative 10, and once again, if we apply ZM, that's going to be correct. So, negative Z2 plus ZM I2 plus ZM I1. ZM is equal to negative 10J. So this is negative 10J. Negative 10J. And this here is supposed to be equal to negative 6. Right? So that's 10, and we're going to need 16. Yes, 16. So Z2 is equal, let me do that in red, 16J. There you go. You just determined Z2. Are there any confusions about that? No? I'm getting a little concerned. I'm not a true professor unless I make at least half of the class confused. Could you redraw the formula where LA is equal L1 minus M, LB is equal L2 minus M, and LC is equal M? Yes, you could. You could. But the issue, the partial issue I have with that is that that formula is specific to that is specific to the aiding circuit. That is specific to aiding. And it's a different formula. I believe you swap the signs there for opposing. So what he's saying is that couldn't the formula just be LA is equal L1 minus M, LB well, this is what I wrote as 1 and 2, is equal L2 minus M, and then LM, or LC, which is my mutual, is equal M. Yes, but my concern is that switches with aiding and opposing, and I'm just really lazy to try doing that. So I just like to do it this way, where you draw it out and you see, because that's what it is. It's an equivalent circuit. You're trying to make a new circuit which provides the same outcome as your original circuit. You can do it that way, if you remember it properly. I'm very forgetful, so I don't. Can you do a quick recap of E after you finish the question? Yeah, sure. So let me just finish this question really quick because we've already figured out the values. So 1 second. Now we just redraw the whole circuit, but with this system instead. So remember how we ignored the rest of the circuit? Now we're bringing it back in, right? So let's redraw the initial circuit parts. So this is still 100 with a phasor of 0. When break? After this. I'm going to take a quick break after this. So 10 minutes probably. We'll see. We have our resistor, still 2 ohms. We have our capacitor, negative 12J. And now we reach our T junction, right? So we have our first inductor. So this is Z1. What is Z1? It is 28J. And it goes down into not an inductor. Our Z mutual is negative 10J. So it's actually a capacitor. Or you can just draw an impedance block. Anyway, negative 10J. Actually, you know what? I'm going to highlight the block. So I'm going to do that. And then our mutual 2, or sorry, our second inductor here is 16J. And then we have the rest of our circuit, which is 5 ohm and 5 ohm, and then 3 ohm. This is our T junction. Is it supposed to be a capacitor? It's a capacitor here because it's negative 10J. Whenever the impedance is negative, that means it's capacitive. If we had determined that Zm is equal to 20J, then it would be an inductor. And you will find it's positive when we have aiding, when the mutual is aiding. What is this transformer? This is just it. This red part is the transformer. This red part, just the red part, is the transformer. The black part is the rest of our original circuit. That's what I'm trying to say. Let's recap here. So if we start at E, we are trying to turn the mutual inductance. Would we lose marks if we put an inductor with negative load? I don't know. I feel like that depends on your TA. Your TA might be picky and take off. I would say most TAs won't care. But a negative reactance is a capacitor. Like, that's what a capacitor is. It's sort of like drawing an inductor with 5 farads. Like, I guess you could treat it as a capacitor, but it should be a capacitor. You shouldn't be drawing an inductor. Anyway, let's go over E. So we wanted to turn our circuit with mutual inductance into a T-junction circuit. Look at this T-junction. That's how it looks like. Right? It's a T. You have 3 reactive loads, Z1, Z2, and Z mutual. It can go by different names, whatever. You can either use that formula method that the other guy was mentioning. Sorry, I forgot your name. I don't know as an insult. Or you can just do equivalence, right? You compare what you get in the mutual circuit. Actually, it'd be better if I, oopsie. if I draw like this, because that is our equivalent circuit. Which is, what are the positive? Okay. Right? So we compare the KVL of this, which is this, to the T junction KVL. And using that, we could compare and find the mutual and Z1. So I1 finds us Z1 and Z mutual. Then we go to I2, and I2 will find us Z2 and Z mutual. This is just KVL, right? It's just KVL. You don't need to really memorize anything. You just need to do KVL of your initial circuit, and then compare it to the KVL of your T junction, and then you figure it out. Right? This stuff is all that you should already know to do. These are both KVL. And then you algebra it. You just solve for it. You have two equations, two unknowns. Actually, it's not even two equations, two unknowns. These are like identical. Here, let me highlight it. You see this here? I'm going to highlight that in green. You see it's times I1. Here you go. These are equivalent. Negative 18 and negative Z1 plus Zm. This here. Let's highlight in blue. There you go. Those two are the same. How is Z2 is equal to 16J? Let me show you. So here, let me highlight this. This is going to be green. And this here on the bottom, let's highlight that in green. And it's going to be blue. Oop. Blue. And it's going to be blue. Oh, no, I did these backwards. Oopsie. There you go. Yes, I can of the whole solution. So now you just match these up. Again, you can find ZM. These are the same. And knowing ZM and these are the same, you can find Z2. What plus the ZM, which is negative 10J, is equal to negative 6. 16. And then, once you have found Z1, Z2, and Zm, you fill it in alongside the rest of the circuit. So I hope that isn't too complicated. Like, I know it's a lot of talking, but it's a couple short steps, really. So if you want the solution for E, let me just write that down here. And then we'll take a quick 10-minute break, because I believe that's the last question on, or sub-question on this one. Yeah, it is. All right. So let's take a 10-minute quick break here, and then we'll move on to the next one. All right. Let me just answer some questions first. How do you know how to do these types of circuits as well? That's the same thing. It's I wouldn't know how you would do oh yeah, no. That would is it's still a parallel circuit. So the only thing is, instead of having it like this, which is what we had, you're now just putting it, connecting them together at the end like this. You still do the same thing. You still do what do you call? You still do all the process that I did before, KVL, mesh analysis, whatever. I don't see where that would be different. Do you have like a specific concern, like what you would do? Yeah, okay. So, just to show, because I can't see. This is the example he showed. He was asking how you would do this, and I'm just saying it's the same process. Okay, let's take a 10-minute break, and then we'll continue on with the other question. And stop recording.